Good day, everyone. I'm Richard Miller, representing Kysor Warren Epta. Thank you so much for letting us participate in the Sustainability Refrigeration Summit. Today, I want to go over one of our case studies employing our patented FTE system. The feedback we receive from customers from time to time is that transcritical booster systems are energy hogs. In the coming slides, we will see what constitutes an FTE system and what you can expect to see in energy costs. To add the simple FTE technology, we start with a standard booster system and we add this FTE tank between the medium temp coils and the medium temp compressors. The vapor that collects at the top of the tank continues on to the medium temp compressors, but the liquid CO2 will collect in the bottom of the FTE tank, thereby allowing us to reduce the superheat on the medium temp compressors. Once we reach an acceptable level of liquid in this tank, we'll be able to shut off the liquid being fed from the gas tank, the flash gas tank, and we'll begin to pull the liquid off the bottom of the FTE tank. And at that point, voila, you're now in full transcritical mode. Case study location is found in the hot and humid zone, and the closest ASHRAE data point is the airport there in Columbus, Georgia, which says that the ASHRAE dry bulb is 96.4 Fahrenheit. So let's take a look at the design conditions. This is a transcritical booster system employing FTE and an air-cooled gas cooler. The design dry bulb and wet bulb are 97 and 78 degrees respectively. The low temperature design set point is -21 and the load is over 68,000 BTU hours. The medium temp design temperature is 19 degrees Fahrenheit and the load is nearly 321,000 BTU hours. And the gas cooler temperature is 120 degrees Fahrenheit. We have the energy data for 1 year, excluding August. We project August to look much like July. The graph goes from September of 2020 through August of 2021. The orange line is the maximum average daily temperature, and the green is the minimum average daily temperature. The black line then is the energy consumption in kilowatt hours for the compressor pack, the gas coolers, and the evaporators. In the top right, you see that there was a spike in the gas cooler consumption, which corresponded to a high dust pollen month, and we had to do some cleaning to free up the gas cooler. The evaporators are seen to be relatively flat during this time. So given the loading criteria, the climate, and assuming energy costs of 10 cents per kilowatt hour, this site saw a yearly energy consumption of $32,731. The compressors accounted for 86% of the system's energy use, but if you include the evaporators, the compressor energy makes up 65% of the total refrigeration cost. This should be scalable, however. So if you have a load that is 120,000 low temp and 650,000 medium temp, then you should expect roughly double these energy costs. Now, obviously, not every store sees the same amount of shoppers and traffic, and more favorable climate conditions yield better energy numbers. But this is just some basic data for one site that we saw in the hot and humid zone. The data is still coming in, but it appears that our standard booster system is 1 to 5% better in energy consumption than traditional HFCs. And adding our patented FTE technology improves the numbers an additional 6 to 10%. I hope this helps you make a comparison to your system's energy, whether it be HFC or transcritical booster. Thank you for your time.